Now, let's take a look at one of MLlib's built-in algorithms, word-to-vector. This algorithm takes in a corpus of text and outputs a featurized set of vectors representing the dictionary of words. The interesting thing about this featurized model is that it can then be used to figure out word similarities. But it's better to see it in action. So here, I've modified our Wikipage word evaluator. I've added an import for the word-to-vec featurizer, and the main method has been turned into a helper method for returning a primed word-to-vec model, which we'll use in the shell to interactively see the abilities of word-to-vec. Then, there are some basic changes to the core code, such as using a different file source containing a larger subset of wiki pages. This time it's about 100 megs worth of data, which should be enough data to provide a meaningful result while still being able to run without needing to spin up a cluster. Then, notice that we're not flattening our wiki data into one big blob, instead keeping them together to help delineate context. These word groupings are often referred to as bags of words. Next, notice the code preparing the word sequences is now also converting everything to lowercase, so they have capitalization in common. However, at this point, it should be noted that this word cleaning is very crude. Outside of proof of concepts, you should probably use a library like NLTK or Natural Language Toolkit to clean and tokenize your words. They handle things like removing stop words, stemming the words down to their word base, and a number of other useful actions. But for now, our simplistic word cleaning should work. And before we get to the bread and butter, we mark our RDD to be cached in memory. Many machine learning algorithms will make multiple passes over the same data, so this memory cache can reduce the processing time by orders of magnitude. Then, once we have our bags of words ready, we can hand it off to MLlib, as all we need to do is instantiate the word-to-vec object and pass our data into its fit method, which returns a word-to-vec model. But before we look at it, I just wanted to take a moment and point out two things. First, the build dependency here follows the same pattern as the other Spark libraries, spark-library name. And second, I'm boosting my shell's memory as many machine learning algorithms require a lot of space and time to work well. Now, refocusing on our primed word model, we can see that it has a number of helpful methods. We can save it for future usage, or even pass in a word to get its vector representation, where vectors are usually the input for other machine learning algorithms. You can even get a map of the word to its corresponding vector representation. But the method we'll start with is the find synonyms method. All we have to do is call this method with either a string or a vector representation of our query, and how many synonyms we'd like back. The return value is an array of tuple2s, with the first slot containing the synonym string, and the second containing how strongly correlated the synonym is to the query. Here, we pass in Spark, and in return, we get items like Databricks, BSD, and Hadoop, which is what we'd expect. Alright, let's try again using Gates. And we're returned Melinda and Bill at the top, followed by a number of influential billionaires just like the Gates. But wait, that's not all. This algorithm can go one step further and figure out analogies. Here, we'll use a stereotypical example. If an emperor is a man, then what's the female version? Note that we're using a helper object to convert our Spark vectors into Breeze vectors, where Breeze is a popular numerical processing library which is used inside of Spark. Here, we'll use it for its ability to perform mathematical operations on vectors, such as addition and subtraction. This allows us to represent our query as a math equation. We take an emperor, remove the man portion, add in a woman, convert that vector representation back to the Spark equivalent, and voila! The model has figured out that we're looking for women royalty titles, with Empress being the most strongly rated. All that simply by passing in a bunch of word bags. I think that's pretty cool. There is a limitation with this algorithm. The query being searched does have to be in the loaded vocabulary, or else it'll throw an exception. However, a lot of the time, this is used for featureization for the next steps, which is outside the scope for this course. And while that's all we'll see for now, it should be noted that while using this growing library of algorithms is making things simpler and simpler, this is still a complex topic, and understanding the output and machine learning practices is still a prerequisite.